Very pleased to have Professor Ron Donagi from the University of Pennsylvania, our newest AGNES node, and he will be speaking to us about moduli of super Riemann surfaces. Can you say something? I didn't hear it.
I think I'm on, right?
Yeah.
Okay, good. Well, it's wonderful being here. What a turnout. I hope you all remember that the next meeting of AGNES is going to be at Penn, and I hope you all come there next fall. So I'm going to assume that not everybody was here for the pre-talk, so I'll go over that a little quickly, and then I'll get into my main talk. Let me start with just a few words of background motivation. This thing comes from string theory, although there will be no string theory in the talk. So, in the oldest version, before M theory, before F theory, before all the fancy stuff, there was perturbative superstrings, where you think of an analog of quantum field theory, where you do a Feynman diagram expansion of some amplitudes and quantities that you want to calculate. And the pictorial trick is you replace a point by a little circle. So a point moving in a line becomes a cylinder, and 2 points merging becomes a pair of pants, and so on. So you end up with the Feynman diagrams being surfaces, with incoming and outgoing circles as the boundaries. And through a few steps, you find that the quantities you want to compute depend only on the conformal structure of the Riemann surface. So you really end up studying things like the moduli of Riemann surfaces, or the moduli Riemann surfaces with endpoints that are marked, so those are the incoming and outgoing particles. As I mentioned in the pre-talk, a notable feature of string theory, two notable features are that it's wrong and it's irrelevant. It's wrong in the sense that it's not consistent, and it's irrelevant because the physics that it predicts has nothing to do with reality. It's superstring theory that's a candidate for a serious theory of physics. And in superstring theory, you need to replace Riemann surfaces by super Riemann surfaces. So I'm going to tell you what those are today. But these are things that formally behave a lot like ordinary Riemann surfaces, except that there's more structure there. So there's a moduli space, let's call it script MG, and there's a moduli space with some marked points, although there are details that are unexpected, such as the marked points come in two varieties. There's Riemann points and Neville-Schwartz points. So there are things that you need to think about, but roughly you could think of this as some sort of variant of moduli spaces. And then the amplitudes that you want to calculate are integrals over script MGM. There has been a plan around, which is people pretty much know what the measure is on ordinary moduli space. And they want to figure out what's the analog of that on supermoduli space. And the obvious plan is to take the forgetful map that takes a super Riemann surface and forgets the structure and gives you the underlying Riemann surface. And take the unknown measure on supermoduli, push it down to ordinary moduli, analyze its growth and qualitative behavior in various limits, and end up with a question about trying to find a modular form of the right level and weight and in order of growth and so on. And in many cases, you can formulate that, and you can find there really is a unique form with those properties. So that seems to be a candidate for the superstring or chiral measure. And it works in low genus, and then it runs into various problems in higher genus. And the theme of my talk, in a word, is that there's a slight complication here, which is that there is no map, no forgetful map, from script M to ordinary M, from the modular superhuman surfaces to the modular ordinary human surfaces. So let me try to make this a little more formal. Jason, how much time do I actually have? When should I end?
I think you have, how much more time or total time? I think about an hour.
Okay, how much more time do I have?
Well, how much more time do you have? About 50 minutes.
50 minutes, okay, so, great. Okay, so I'm going to tell you what supermanifolds are. I'm going to tell you a little bit about the obstruction theory for supermanifolds. Then we'll start talking about super-Riemann surfaces, which are the lowest dimensional supermanifolds, together with some extra structure which makes them supersymmetric as opposed to just supermanifolds.
So there are no supermanifolds of dimension 0?
Well, there are, but they're not very interesting. So if you can hold for about 10 minutes, I'll tell you exactly what happens in low dimensions. You'll see. So they're there, but they're pretty boring. Okay, then I'll tell you a little bit about supermoduli spaces. I'll state the main results, and depending on how time goes, I might give some ideas from proof. It would be especially nice if I can sketch a little bit of the obstruction theory for super-Riemann surfaces. It's a very pretty story, I think. Okay, so let's start with a split supermanifold. A split supermanifold is a supercommutative locally ringed space. Supercommutative means Z2 graded commutative. So you have a sheaf that's Z2 graded, and the commutation is just like the commutation of differential forms. Two odd forms anti-commute, everything else commutes. So you want a space M in a structure sheaf OS, where M is just a manifold, and OS is going to be the structure sheaf of M handled with an exterior algebra. And the Z2 grading comes from the dot, the number of vectors that you're wedging together. With these, any vector button M. So this is going to be an example of a supermanifold. It will be a split supermanifold. A supermanifold in general is going to be a supercommutative locally ringed space, which is locally isomorphic to one of the above. So locally it looks like OM tensor wedge dot V dual, but the isomorphism is only local, so the vector bundle itself doesn't have to patch together. Well, that's not quite true. Well, let's just introduce the notation. I have the manifold M and the bundle V, which I think of as a normal bundle or an odd tangent bundle. So let M be the dimension of M and N be the rank of V. So the dimension of the supermanifold is going to be the pair consisting of M, the even dimension, and N, the odd dimension.
Is M a complex manifold or just
Right. So the options are N can be C infinity or holomorphic or algebraic or any other category that you want to work with. So you have all these variants of supermanifolds. And the underlying field, well, it could be any field. In particular, it could be the reals or the complexes. The thing that's the most useful in, at least in heterotic string theory, is actually some hybrid between that. Roughly, you want complex vector bundles on real manifolds, on real underlying manifolds. So complex, odd, and real even. But we don't need to know about that in this talk. So that's what the CS stands for. Complex Superman. Forget what it stands for, but it's supposed to be this hybrid where it's real in one direction and complex in the other. Anyway, so I said that the bundle V doesn't quite patch together. That is not true. The supermanifold S does determine both M and V. The formal way to say it is that the structure sheaf contains the maximum nilpotent ideal. The ideal of all nilpotents in the structure sheaf, which, if the thing were split, so that it was just an exterior algebra, it would be everything except for the grade 0 piece. So this J makes sense in general, and you can look at the manifold that you get by taking the graded version of OS with respect to the powers of J. So GER 0, that's OS divided by J, that is just OM. So this way you recover the manifold M from S. And similarly, if you take J mod J squared, the first graded piece, that gives you, well, the dual of V. So you can recover V and M from S. And to capture the situation, the supermanifold S determines a graded version of S, which is a split supermanifold. Knowing the split supermanifold is equivalent to knowing a manifold in a bundle. You can always go back, but you cannot go back here. There may be many different supermanifold S with the same graded version. And the obstruction theory is exactly an attempt to measure how far we are from splitting. In terms of notation, I'll use Latin letters like X's or Z's for the coordinates on M, and Greek letters like thetas for the odd directions, coordinates in the odd directions. Okay. So, between the I guess I should have said, M is always some supermanifold. In fact, if you can still see it here. M always embeds into S. And you see that from the fact that at the structure sheet level it goes the other way. OM was a quotient of OS. So that means that you have an inclusion this way. But there's no reason to have a projection here, meaning a map of OM back into OS. Locally you do, but globally you may not. So if you do, you say that S is projected. So being projected is somewhere in between being split and being just a general supermanifold. So it's 3 levels of complexity of the supermanifold. The split ones are ones that I consider to be essentially trivial to answer Dan's question. So not that they don't exist, but they're going to be split in order if you don't have enough room to maneuver. So we just ignore them. Okay. So between the manifold and the supermanifold, you can stratify things by these SIs, where SI is always the same topological space, M, but with different sheaves. You take the sheaf to be the full structure sheaf where you kill anything that includes I plus 1 or more nilpotents. So you leave up to I nilpotents, but no more. So you have this inclusion, so you can think of it as a stratification. The ordinary algebraic geometry analog of this is that S is a manifold, a smooth scheme. So is M. All the things in between are not. They are something like everywhere non-reduced schemes. Because, well, they don't look like exterior algebra, they're truncated exterior algebras. But nevertheless, you can do geometry of those things. In particular, you can ask the question of a splitting or a projection of S to M step by step. So S0 is M, it's always split. So you can ask, is S1 split? And if it is, can you look at the splitting of S2 and so on? And if you look at Mani's book on gauge theory and complex geometry, he approaches the story exactly this way, and he derives the sequence of obstruction classes phi I, where omega of phi I, which is the obstruction given a splitting or projection phi I, the obstruction for lifting it to the next step. And he calculates and he sees that it's always an H1 class. It's H1 of M with values in something like the tangent bundle of M, tensor the I plus first power of the dual of V. And the 0 here tells you that you will get an even grade piece of that at the end. So in particular, well, you can do a check version of it, and I describe it here, but I don't think it'll be terribly useful to describe it. You can write down an open cover. Let's say we're in the algebraic world, so you use a Zariski open cover. And on that, your supermanifolds are always split, and then you're measuring the obstruction to piecing things together, and it always ends up in H1. You convince yourself that this is the bundle where it lives. So these things that I'm writing, you convince yourself that they're derivations. That's where you get the TM copy. And then it's always even. That's why we have the 0 here. and it's a cocyclic, so it gives you an analytic cohomology. Unfortunately, beyond the first obstruction, the other ones seem to be very vaguely defined. They depend not just on the manifold, but on how you chose your trivialization at the previous steps. So we've been having trouble coming up with a really convincing theory of higher obstruction. I'd like to suggest that as a first big gap in supergeometry. We don't have a really convincing candidate for a full obstruction theory. But nevertheless, just having these classes is tremendously powerful. So here's some correlates. So if you're working in the C infinity category, any C infinity supermanifold is split. Because C infinity is isomorphic to its greatest version. And that's simply because every C infinity locally free sheet is fine, so all the higher cohomology vanishes, so there's no place for the obstructions to live. So all the obstructions vanish, and the thing is going to be split. So let's restrict attention to the algebraic or holomorphic one. So let's say the dimension of S is m/1, just one odd direction. So V is a line run. Well, then again, S is automatically going to be split, because the first obstruction lives in wedge 2 of V, and V is a line bundle. There is no wedge 2, and there's no place for the thing to live. So all the obstructions vanish. When the dimension is m/2, that's the smallest place where you can have a non-trivial object. And in fact, you can convince yourself that in this case, S is determined by the triple, not by the pair M and V, but the triple M and V and the first obstruction class omega. And these are arbitrary. So given any class omega in H1, blah, 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 you get a unique supermanifold with that obstruction class. So that gives you a quantitative way of saying how far this diagram back here was from being reversible. The distance between the S's and the split S's is a particular first cohomology group. But that's only when the odd direction n is 2. When it's higher, as I said, we do not have a complete obstruction theory. We don't have a really good way to describe the ambiguity. This also lets you write down your first examples of non-split objects. So the easiest one is take a conic. So what's a conic in P2? You take coordinates x, y, z, and you write something like x squared plus y squared plus z squared equals 0. Now we make it supersymmetric, but instead of working in P2, we go to P2/2. So P2/2 is roughly C3/2. A vector space with 3 even directions and 2 odd directions. And you divide by 1 C star acting the C star is just the usual even C star. It acts uniformly on both coordinates. So you have to think a little bit about how to write local coordinates there. But it's something that has coordinates x, y, z, where only their ratios make sense. And let's say theta 1 and theta 2, which are odd. And again, things like theta 1 over x makes sense globally. Theta 1 is not invariant, just as x is not invariant. So you can write down something like x squared plus y squared plus z squared plus, well, I can't do theta 1 squared, because theta is nilpotent, but I can do theta 1, theta 2. So this is the simplest way to write down a non-degenerate submanifold P22. So this is your basic conic. It's homogeneous in degree 2. It's just a conic in the superplane. And you calculate the omega class for it, and it's easy to see that it's non-zero. So this one already is non-split. The underlying manifold is just the ordinary conic. It contains it, but there's no projection back. Okay. Well, as I said, this obstruction theory is quite powerful. It gives you a lot of stuff. So, for example, it gives you an iterative picture of the space of all splittings. So, given a supermanifold S, if it is split, it's not split uniquely. You can ask, what's the space of all splittings? And the answer is it's an iterative separation by affine spaces. So when, in the case that the odd part was 2, it was just an affine space. In general, it's going to be it'll have some iterated figuration structure. And also you can convince yourself that the action of the automorphisms of S preserves this figuration. So from that you can deduce, for example, that if S is an algebraic supermanifold and F is any reductive group of automorphisms acting on it, then if S is split, it is automatically equivariantly split. And it follows from the fact that actions on affine spaces have fixed points and you do an inductive argument. So, if you don't know what a reductive group is, never mind, just take it to be fine. So, let's say pi is a finite covering map between supermanifolds. It's a local isomorphism, and topologically it's a finite covering. If S is split or projected, then so is S tilde. If S tilde is split, so is S. If it's projected, I think it's false. I didn't actually check that carefully. At least the proof doesn't work for projected. So that follows by finding an equivariant splitting in plane. Then there are various compatibility results. I'm not going to bother with the details. Let's just go to the last corollary. If M prime is a sub-supermanifold, that's a mouthful. I'll just say submanifold. M prime is contained in M, and they're both supermanifolds. I can take the tangent bundle of M and restrict it to M prime. So there will be a little short exact sequence involving the tangent of M prime and the normal bundle. Let's assume that that sequence splits. So it's a direct sum. And let's say that you know that the first obstruction for... So S prime is some supermanifold whose underlying manifold is M prime. And S is a supermanifold whose underlying manifold is M. If the obstruction for S prime is non-zero, I can then deduce that the obstruction for the larger manifold is non-zero. So in other words, if I have a supermanifold, and I want to show that it's non-split, it's enough to exhibit a small sub-supermanifold, which is not split, but I have this technicality, I need to know that the normal sequence splits. If it does, then just by looking at where omega lives, you can see that the group where omega 2s prime lives is going to be a subspace of the group for omega 2 of s. So you have an injection. So the fact that one of them is not zero tells you that the larger one. Without the assumption, you have some complicated spiral sequence and you lose control. So let's remember this because this is going to be a key step in the proof. Okay, so those were supermanifolds. What I need are supersymmetric manifolds. And the supersymmetric manifolds I'll deal with are super-Riemann surfaces. So here's the definition. A super-Riemann surface is a complex supermanifold of dimension 1/1, one even complex direction and one odd complex direction, together with a maximally non-integrable odd distribution. Which means what? Well, a distribution is a subbundle of the tangent bundle. The tangent bundle here is, well, I'd like to say rank 2, but I really should say it's rank 1/1, generated by ddx and dd theta. If you have a vector like ddx and you bracket it with itself, it gives you 0. So, but in the odd directions, you can have things that are non-integrable. So here's an example. Take v to be dd theta plus theta ddx. Think of that as an operator. It takes functions to functions, the derivation. Let's do it twice. So what does a general function on this manifold look like? It looks like a function of x plus theta times another function of x. And that's it. You don't have a theta squared. So every function has component fields, an even one and an odd one, an f and a g. If I apply this particular vector field to it, what do I get? The dd theta part kills the theta, it just gives me a g. While the ddx, you'd think that it acts on both of them, But the fact that I'm multiplying by theta kills the coefficient of theta and gives me only the derivative of f. So if I apply the vector field once, I get g plus theta f prime. Right? So do it again. You change places again, and differentiate the other guy, and you get f prime plus theta g prime. In other words, this vector field applied twice in a row is ddx. It just gives you the x derivative. So this is a spinorial derivative. It's an operator whose square is the first derivative, the thing that corresponds to translations on demand. So it's the square root of the translation operator. And the fact that this is nowhere zero, that is what makes this a super-Riemann surface. So I should say, for vector fields, you would take the commutant for unit vectors. For all vector fields, you would take the anti-commutant, which is just twice the square. So saying that it's non-integrable just says that its square is non-zero. And that's what I showed you. The square is non-zero. The square of this thing is ddx. So a super-Riemann surface is a complex supermanifold together with a subbundle of the tangent bundle, which is purely odd, so it's generated by one odd vector field, such that it's the square of that vector field is everywhere non-zero, or its bracket towards itself is non-zero. Or equivalently, lemma. There exist local coordinates x and theta such that it looks exactly like the thing I wrote. So there's a Darboux lemma that says it has to look like this. So notice that the underlying supermanifold itself is split. The manifold M is a Riemann surface, and V is going to be a line bundle. In fact, it's going to be a square root of the tangent or cotangent bundle, depending on how you normalize things. The fact that V squared is ddx tells you that your tangent direction, your odd tangent direction is the square root of the tangent bundle. Or clearly its dual is a theta curvature, a square root of the canonical bundle. In topology, they call it spin structures, and in algebraic geometry, we call it theta curvature. So the underlying topological data is a Riemann surface with a theta curvature, not geometric data. Okay. But somehow the point is that there isn't enough information. By talking about the M and the V, you're remembering the bosonic moduli of your super-Riemann surface. But it also depends on odd coordinates, and that's the whole point. So the more interesting issue is to deal not with a single super-Riemann surface, but with a family of super-Riemann surfaces, specifically with families where the base is odd, or at least contains odd directions. Even families of super-Riemann surfaces are not so interesting. It's always the odd families that are going to be interesting. So remember, whenever we deal with a super-Riemann surface, there's always a spin structure that's pre-chosen. So it seems safe to call it square root of Tn, or Tn to the power 1/2. So I can talk about powers of T, where the power is not just an integer, but also a half integer. So to make a long story short, supermodular spaces exist, and they have roughly the same properties that ordinary modular spaces have. There is a modular space of super-Riemann surfaces. It is a supermanifold, if you believe that ordinary modular space is a manifold. And if not, you can make it a super-orbifold, and then there's another object which is a super-stack, and you can make sense of all of these. And the behavior is roughly the same as that of ordinary manifolds. The only interesting difference is that if you have, well, it's smooth as a stack, not as a manifold. Just like a modular space of ordinary Riemann surfaces is not smooth. The space is not smooth. The stack is smooth. So it's the exact statement holds for the supermanifold. So Mg as a manifold, or as a space, is smooth away from Riemann surfaces or curves with an extra automorphism. Okay? That's the locus where things are bad. How about MG? It's the same, but notice that if the local coordinates are x and theta, I can send that to x and negative theta. So there's always a non-trivial automorphism for every super-Riemann surface. Every super-Riemann surface over a point. So this becomes false if you work over all directions. But if you just talk about one super-Riemann surface over a point has automorphisms. So the moduli superspace behaves more like what you are used to in genus 2, where every Riemann surface is hyperelliptic. And this should not be called hyperelliptic, because on the topology this acts completely trivial. The action is only on the odd direction. But this does come into the stack destruction. So the stack that you get has a Z2, a non-trivial Z2 everywhere. Okay? So it's slightly richer than the ordinary story, but very parallel. So we said that a supermanifold has a pair of dimensions. What is the dimension of supermoduli? Well, it's a pair of numbers. The even dimension is just the dimension of the underlying manifold, which is 3g minus 3. The odd part turns out to be 2g minus 3. And in fact, I can tell you, and did right there, what the tangent and cotangent spaces are. The even part of the tangent space is h1 of the tangent bundle of the underlying Riemann surface. Or in other words, the cotangent is quadratic differentials. The odd part is going to be h1 of the odd tangent bundle, which is the square root of the usual tangent. And therefore the dual, by usual singularity or usual curve, is going to be the sesquilinear differentials. Sections of the 3/2 power of k. What does that mean? It means the third power of the chosen square root of k. So you know exactly what that means. So you know the dimensions, in fact you know what the tangent and cotangent spaces are. And let me emphasize that the reduced space, the topological space underlying strip MG is not MG. Because there's this little bit of topological data that's chosen. A super-Riemann surface, the terms of Riemann surface, and a theta characteristic on it. So it's just the spin moduli space, the moduli space of Riemann surfaces with a theta characteristic on it. That is the... In particular, it's disconnected. It has two components. There's even and odd theta characteristics. Or even and odd spin structures. Okay. So the theorem is that supermoduli space is not split when the genus is 5 or half. And there are about 6-7 papers by Witten, and by now it's up to 10 from the last few years on the archive, where he talks, among other things, about the relevance of this thing to superstring perturbation theory. There is a marked version of this thing. Actually, in the papers, we only looked at Neville-Schwartz punctures. One ought to look at the Riemann punctures as well. And they tend to behave very differently. So, for any n, there exists mg in Neville-Schwartz in Riemann. So you specify the number of Neville-Schwartz punctures and the number of Riemann punctures, and I haven't told you exactly what they are. A Neville-Schwartz puncture is pretty much your idea of a puncture, just a point on the super-Riemann surface. A Riemann puncture is something that's a little trickier. let me just say, if you have a Riemann surface C together with these punctures, the canonical bundle of C, whatever that means, is going to be the super-canonical bundle, which usually is called the Berezinian of the C, is going to be the square root of the canonical bundle of C. That's what you get if you have no marked points. If you have Neveu-Schwarz points, they still don't affect anything. But you need to twist by the Riemann points. So the Riemann points actually, I guess you can do them as non-crecums, and they affect the canonical bundle. So one thing you see immediately is that the number of Riemann punctures has to be even. You cannot take a square root of an odd degree bundle. So there is no such thing as a super-Riemann surface with a single Riemann puncture, or not a compact. Another thing you see from this is that you can forget a Neveu-Schwarz puncture, just like on an ordinary Riemann surface, you can forget a puncture. You have a map from MGN, forget from map to MG. You forget the punctures. Similarly, we have a map from MG. We can forget the Neveu-Schwarz punctures, but we cannot forget the Riemann punctures, because the data is different. As long as you keep your Riemann punctures, the square root is the square root of the same thing. But if you try to drop them, you don't have a natural choice. A square root of a twisted version of a canonical bundle does not determine a square root of a canonical bundle, vice versa. So you can forget a Neveu-Schwarz puncture. The space with marked Neveu-Schwarz punctures is a bundle over the underlying one. But the space with Riemann punctures contains it rather than fibering over it. So it's a different picture. Nevertheless, both of them are essential for any geometric approach to these moduli spaces. In particular, we look at the moduli with some number of Neveu-Schwarz punctures, and we show that this thing is not split already when the genus is 2 or more, as long as you have one puncture. And then there are various other results when you have more than one puncture. That would bother you. So, so they have about 18 minutes?
A little more than that.
A little more than that. Great. Okay. So, we actually prove the statement about MG1 first, and then we use that to prove the statement about MG. So, I already told you that one way to show that the supermanifold is not split is to find something sitting inside it that's not split. But then you need this extra condition that the normal bundle decomposes. I mean, the normal sequence that decomposes. So maybe we can just find a compact curve B inside moduli space, take omega, the obstruction class, restrict it to B, calculate, show that it's not 0. Maybe show something about the normal sequence, and we win. Well, that's roughly the idea. You need to add a few more details here. So, the first thing that I'm going to do is I'm going to show you an interpretation, a concrete interpretation of what the obstruction is for the modular super-Riemann surfaces. And we'll do that. Then we have to describe some families of compact Riemann surfaces in MG. It turns out that it doesn't make sense to look just at one. We may as well look at an entire family. So we're going to look at maps from one moduli space to another. So we're going to look at modular maps like that. Then we'll give a basic example of the non-split supermanifold. The dimension will be 1/2. The 1 will correspond to the Riemann surface. I'll show you the two operations. And by jazzing that up, we'll show that MG1 is non-split when the genus is at least 2. And then I'll show you how to embed MG1, maybe with some étale cover, into MG tilde for any G tilde that's 5 or more. And then we show that the normal sequence splits, so we conclude that the big space is not split. So let me at least show you a little bit. Let me show you an explicit version of the obstruction for superhuman surface. So where should it live? The first obstruction to splitting of anything is class omega in H1 of the underlying reduced space, which in this case is the spin moduli space, with values in whatever, half, wedge, 2t minus, t plus. We interpret an H1 class as an extension. So there's x1. So it's an extension of wedge 2t minus by t plus. So I need to give you a God-given extension like this that lives over the entire modular space. It's programmed. In the original version I had a red dot and a blue dot. I'm afraid they look exactly the same. Yeah, so use your imagination. Anyway, dually, just put duals on everything and switch places. It'll be a little easier to see it that way. So fix a curve C and a spin structure. So it's point of the spin modular space. Look at the surface C cross C. This is a two complex dimensional surface, real dimension form. Look at the surface C cross C, and on it, what are the sheaves that we can consider? So there are 3 natural sheaves that I can consider on that surface. So I can have the projection on the first component, upper star of something on K, right here. That's something on C, canonical bundle. And I can take the projection on the second factor of K. And then another natural line bundle here comes from the divisor, which is the diagonal. So take some arbitrary linear combination of these 3. Well, let's remember we are on the super-Riemann surface, so we can do a little better than K. There's a natural square root of K. So let's define O of ABC to be the 8th power of this, and the bth power of that, and the cth power of that. I hope that's what I wrote up there. Yes. So O of ABC will be that thing. I forgot the O there. Well, P1 and P2 are the projections, and delta is the end. Okay. So now, let's look at the restriction sequence. So we have delta sits inside C cross C. So I have the restriction, and here it is. It goes from O of ABC to something, and the kernel is O of A, B, C minus 1. You allow a pole on the diagonal go to 1 less. And that's the kernel of restriction to the diagonal, and you just have to calculate what you get. It's a line bundle on the diagonal, which is identified with C. It turns out to be K to the power half of A plus B minus twice C. I'll leave that for you to check. So we'll call that the sequence number ABC. So I claim the fiber of one of these dots, the thing that I want, the class of the obstruction class, can be identified with the H0 sequence of this for a particular set of numbers ABC, namely 3, 3, and 1. In other words, I take the 3 halves power here, and the 3 halves power here, and the 1 power here, and I tensor them. That's going to be the thing in the middle. And then I take the restriction sequence, which is also the residue sequence, so you can just call it RES, and leave the interpretation open. And then there's the dual description, which involves some higher cohomologies for some other sheaf. So what I'm really saying is, I want a class in H1 of moduli space. That means an extension. That means that at each point, for each Superhuman surface, I need a natural extension. For each Superhuman surface, For each particular superhuman surface, the extension is just an extension of vector spaces, and it splits. But I should think of this as the fiber of a sequence of bundles over the whole moduli space, and that sequence will not split. Well, that's what I need to show, that that sequence does not split. But what I'm saying at this point is, this is a concrete identification of what this thing will be. It will be the obstruction class turns out to be exactly this extension. And again, I'm cheating a little bit. You have to use the fact that there's an involution I, it's at point xy to yx, and it acts on the sheaves and on the cohomology. And you need to decompose everything into even and odd parts with respect to this and take the right piece. So I'm sweeping a little bit of stuff under the right. But let me not focus on that. All right, so I might tell you something about the compact curves that I need, but let me switch gears a little. And I want to put these obstruction classes in a context. This is a new paper that's going to be on the web on Sunday. So omega, the first obstruction class, is an H1 of this thing. It's an extension class between these two bundles, as I was just saying. Okay. I can give several interpretations of it. One interpretation is in terms of rings of differential operators. I can interpret the obstruction as an extension class encoded in the rings of those ith-order differential operators on a supermanifold whose symbol is purely odd, involves only, the highest degree piece of the differential operator is purely odd. So more precisely, there's V2S, and the odd part of V2 and the odd part of V1. And if you write them down and you take the quotient, that turns out to be just the right extension. So that's one way to interpret it. Another way to interpret it is in terms of the higher deformation theory. First order deformations are easy. Second order deformations were made by the devil. They become non-abelian and they confuse you no end. But it turned out that the set of second order deformations of a point in a supermanifold has the structure of an affine bundle. It lives over two copies of the ordinary tangent bundle, but then there's an extension using the odd-tangent bundle. So the second interpretation is that it's the class of that affine bundle is the obstruction in general. And then you notice that all these words sound familiar. There's something called the Atiyah class of a vector bundle, which is the obstruction to having a connection of that bundle. So again, there are all these different categories. You can do it to infinity, you can do it holomorphically. In any one of those categories, you can say, given a manifold in a bundle, does the bundle have a connection? Well, in some theories, it'll be trivially true, and in others not. The class that controls that is the Atiyah class. The set of all local connections is itself an affine bundle of the manifold, modeled on one-forms tensored with the homomorphisms of the bundle. So H1 of that contains the obstruction to having a global section, which would be a connection. So existence of connection is obstructed by the Atiyah class. And it's a very powerful invariant because its trace is the first Chern class. If you square it and take the trace, you get the second Chern class and so on. All the Chern classes are encoded in it in a lot more, as I say here. So there's a lovely paper by Misha Kaprano where he shows that the Atiyah class has interpretations that are very simple. There's an interpretation of the Atiyah class in terms of the ring of differential operators. There's an interpretation in terms of second order deformation theory. So why is this? Why is there an analogy between the obstruction class and the Atiyah class? And what we show is Here's the result about the super-Atiyah class. The super-Atiyah, so the answer is there is a thing called the super-Atiyah class. So given a super-manifold and a super-bundle on it, you can define its super-Atiyah class. So I've just added super-derivative, that's pretty boring. The more interesting part of the story are the ones where you really have to notice some new features. The super-Atiyah class itself is an irreducible piece, but if you restrict it to the ordinary underlying manifold, it splits into pieces. 3 pieces to be precise, just by just count even and odd types and stuff. So the super-Atiyah class has these descriptions in terms of differential operators and deformations, but when you restrict it back to the even part, to M, you get this decomposition highlighted here. So H1 on M of Hom from sim 2 TS to TS. This is the group where the super-Atiyah class lives. This is the super-Atiyah class with the super-tangent bundle of the super-manifold S. And you just show that this cohomology breaks into 3 pieces. One is H1 of Hom, sim to T plus to T plus, and then the thing involving T minus to T minus, and then mixed term in that. The theorem says that these 3 pieces have interpretations. The first 2, well, one of them is the Atiyah class of the even tangent bundle. This would be the ordinary Atiyah class of the odd tangent bundle. And then there's a 3rd piece, and that turns out to be exactly the obstruction class to the split of the schematic. So this tells me that the obstruction class is some sort of a twisted version of the Atiyah class. In fact, it's a component of the super-Atiyah class. And that's why one ends up with similar characterization of the obstruction class in the Atiyah class. Alright, so I think I can put this one. No. Okay. So, what curve are we going to find inside Moduli space? You want to find a compact curve inside Moduli space such that you have a chance of calculating things explicitly on that curve. That curve is a curve in Moduli space, so you think of it as a family of super-Riemann surfaces. Are the compact curves in Moduli? Well, you might know that already. Satake, Atiyah, Kodara, Hirtzberg gave various examples of those things. The reason that they exist is that even though Moduli space is not compact, it has a Satake compactification whose boundary is very small. So a generic linear subspace is going to miss the boundary and give you something compact inside. You give those estimates of the dimension of themselves. So it's easy to find curves. Atiyah, Kodara, and Hirtzberg gave various explicit examples of those. Unfortunately, those are completely useless to us. The reason is the following. If, let's say S is a super-Riemann surface with underlying reduced manifold C, okay, and you have some covering C tilde of the C, then you can ask, can you construct a corresponding cover S tilde of S whose reduced structure would be C tilde? And the answer is yes. There's no problem with it. If this is a covering. What about if this is a branch covering? Then the answer is no. Because to get a super something, at least you should be able to get a theta, a square root of the canonical class of C tilde is going to be the pullback of the canonical bundle C, twisted by the ramification. So if you are given a superstructure in C, all you're given is the square root of K. But there's nothing that tells you how to find the square root of the twist part. So there's no natural way to that. In general, there will be no way. The only exception is this will be okay if the ramification is given to you as an even divisor, meaning that the number of sheets that come together, each ramification point has to be odd by a junction. Right? You're twisting by the order of ramification minus 1. That's the contribution to the connection. So all those examples of Atiyah, Donagi, and Stony Brook, or the ones you get from generic linear sections a la Satake, are going to be obtained by starting with some curve, constructing a family of covers where the cover moves in some clever way. But these covers always have even, or just ordinary ramification, 2 points, 2 sheets coming together. So you have to come up with a variant of these constructions where, this strange condition that only odd, well, order 3 is what you do. So you want to allow only 3 sheets to come together, never 2. So here's one particular way to do it. We start with a curve of genus 2. That's the 2 in our MG1. So that's why Atiyah starts at 2. And we construct a family of triple covers with a single branch point. Believe it or not, you can do it. It's kind of confusing, but there's something called oops, that's what it's called. The standard construction of a branch cover with a single branch point. You can't do it with double cover because some with order 2 or with normal. And you can construct a non-abelian cover of the degree 3 branch with a single point. And you just play around with it and you count the moduli. And I end up with some diagram like this where the basic ingredient is I start with P1. I look at an elliptic curve and a genus 2 curve and another rational curve. So this one is branched with 2 branch points. This has 4 branch points. This is all 6. You take a common fiber product. And then you move the points in just the right condition. You end up with a curve B of genus 19, which parameterizes these triple covers where you've cleverly avoided 2 sheets coming together. You only have 3 sheets coming together. In fact, even though the base is genus 19, when you map it into moduli, it turns out that the map is not 1 to 1. And the image is actually going to be a rational curve. So it actually produces rational curves in modular space, which is not completely new. I found that to be rather surprising that these things exist. So it exist compact rational curves in M5 and in higher spaces. So basically this is the Atiyah class gives us a proof that MG1 is non-split by fielding some basic example, which I better not get into, in forming it. We show that, so MG1 itself contains compact curves, right? Because you can just fix a curve and just move the point on it. So basically that compact curve is going to be the one that we use for the calculation to show that the omega is not there. And then we use this trick with triple covers to embed M2, 1 into M5 or MG from G bigger than or equal to 5. And then we show that some normal sequence is non-split, and that gives the results. Let's see a whole bunch. Let me just So here's the review. The first obstruction to projectedness or splitness of the moduli space is this omega in H1 of a Hall. This is the class of an extension involving vector bundles on the span moduli space. And we identify exactly what these bundles are, and we give an explicit interpretation of this class as global sections on C cross C of some particular sequence that's called star sub 3, 3, whatever. But we have an explicit sequence of meromorphic differentials on the surface C cross C that contributes to this class. We calculate it explicitly in this one example, M21, and we show that it's non-zero on it. In fact, its restriction to 1/5 of M21 over M2 is already non-zero. Then we find this embedding of M21, or some top cover of it, into MG, when G is bigger than 5, and that's what's done with these triple cover, with these covers with all degree orientation, and then we're able to show that the tangent space decomposes into the tangent and normal bundle. So it's not an extension, it's a direct sum decomposition. So we can restrict the tangential part to the tangential part, and this is identified with the corresponding extension from M21 tilde, which we already showed was non-zero, and that's how we showed that the moduli space, and G itself is non-zero. So what I really wanted to say was that supermoduli spaces such as the script MG and MG1 and so on are new objects. They cannot be really described by traditional algebraic geometry techniques, although the flavor of what you do with them is very algebraic geometric. And there are lots and lots of open questions about them nobody's ever looked at. And the obvious exercise to do is to take your favorite chapter in Algebraic Theories and try to add the word super there, and you'll see right away there are a lot of places where you're not just adding the word super, you have to think seriously about what these things mean. The other conclusion I'd like to propose is that algebraic geometry provides a powerful toolkit for studying questions about moduli spaces that seem to be relevant for string theory. But supermoduli space is also an object of great beauty and depth in its own, regardless of the applications of physics, and it deserves probably as much attention as ordinary moduli spaces deserve. So, thank you.
Questions? So is there a theory of alternative compactification? Or is there a Deligne-Mumford compactification of this supermoduli space?
Absolutely, yeah. There is a Deligne-Mumford compactification, and it has a boundary which has, first of all, it separates into the Neveu-Schwarz part and the Riemann part, but then you have normal crossing and basically all the properties that you expect from the ordinary Deligne-Mumford. They do go through. And Whittle describes it in two of the recent papers. This was developed by Deligne 20 years ago, but he never published it.
So for this special triple ramification that you take, can you study a case of cover, like a perfect scheme, super-perfect scheme of covers of this that I would then expect to be non-split over the usual perfect scheme?
I'll have to unravel that. I think that at some level that is what we do. We're looking at the family of all covers with a particular pattern, and at the time by the time we look at it, we've already tossed out all the super, and we're just left with construction questions and ordinary moduli spaces. But I think it's equivalent to constructing superhuman schemes. And presumably there are integral systems associated to them, and the whole story should be.
In the case of a non-branch cover of C tilde over C, I suppose, how does the construction of S tilde work? Like, is it uniquely determined?
Well, let's think about it. What do we need? So we are given S and C tilde now. To construct this tilde, we need to know what's the underlying manifold and what's the sheaf of functions of it. The manifold we have. What's the sheaf of function? You just take the pullback of this sheaf. S is essentially a sheaf called C, and you just pull it back here. The problem about verification is that the maximal non-degeneracy of your distribution is going to fail. So you do get a supermanifold, but it's not supersymmetric. You'll have the wrong local form for the spin.
Is there a different stage on this?
One can guess. As far as I know, nobody's ever looked at that. So try to make a great thesis for someone. Pardon? What about superhumans?
Is there superpowers?
Again, it's easy to just say super this or that. The question is not can you define it, are these objects interesting? And I don't know the answer. It seems like there's a lot of room to ask questions, and some of them are just going to be boring or trivial, and others seem to really introduce new ideas. I cannot tell which is which. People have looked, for example, at trying to construct superhybrid schemes. And apparently there are all kinds of non-obvious issues about when are they going to be projective and when not. And I don't know the definitive answer, but Sherman captured some examples where things that you think should be projective are not projective. So, as far as I know, that's wide open.
Well, let's thank Professor Donagi again.